Now again, I just want to actually bring your attention to a different form that's on your formula sheet. And the form that's on your formula sheet looks a bit like this. Okay, so this is the form found on your formula sheet. So what's going on here? Why do these all look kind of different? Again, they're just kind of different ways of writing a similar statement, right? If we in fact have the derivative of the denominator on the numerator, that's actually how we define the derivative of the log function. We can straight up just integrate it and write it in that form. So make sure you go check back on your derivatives of logs if that's something you're not too confident about. But that was kind of our definition of the derivative, right? So it makes sense that we could go straight back to this expression here. What that means is, if I ever have a situation where I have the derivative of the denominator on the numerator, then I can just integrate. That's actually what you're doing over here, right? Because you've got x, and you take the derivative, you get 1. That's why we can straight up just integrate as the log of x, okay? So when I'm doing this, right, it allows me to access more kinds of functions now. This is why I suspect they've written this form in your reference sheet, right? So if I wanted to find, what are we up to? Example 5, right? If I wanted to find the integral of this expression here, right? I'd see, hey, hang on, it doesn't seem to match up with any of these forms because it's not a linear function anymore. But if I check the derivative of this denominator, right, if this is my f of x, and I took the derivative of that, f dash of x, that would just be, well, that's 2x, and that becomes 1. I do have 2x plus 1 over here. I could just integrate that immediately as, well, that would be ln of x squared plus x plus any constants there, right? So that's just something to be aware of. And similarly, if I needed to do something a bit more complicated, if I needed to do some rearranging, I can do that as well. So I've got an example for you. What if I had something like this? Okay, so I've got a different kind of expression here. Same idea there, right? If I can somehow find the derivative of the denominator on the numerator, then that's what I'm really looking to get. So if you check f of x here on the denominator, and you say, well, again, it doesn't match any of the forms, but if I check the derivative, I end up getting, so I take the derivative, this just goes away. This is 4x over here, so that becomes 4, and minus 3x squared, sorry, it's a terrible x squared, it becomes minus 6x. So you can see, again, it looks very similar to what you've got in the numerator. What am I missing? Well, I'm just missing the fact that this is double this expression. So what I'm going to do is, okay, I want to double it. I need to multiply by 2. But going back to this idea of undoing operations, I want to do the opposite of that to make sure I'm not changing the expression at all. If I just divide by 2, then that would cancel that out. But another way of writing that is multiplying by half. So I'm just going to put that at the front there. Okay. So I haven't changed the expression at all, but I've written in such a way that now I have the numerator, the derivative of the denominator on the numerator, right? So I could actually integrate straight from this form. So these two are the same thing, just to make that clear. Once I've got that, then I can just say, well, that means I can now integrate. I've got ln, half ln of this expression here. Okay. And then plus any constants. Okay. So that's integrals of indefinite integrals involving logs.